All right. Thank you for inviting me and having me to speak. So the first thing I want to say is happy birthday to Rod. Second thing I want to say is this is all joint work with Turbo Ho. So the main question I'm going to talk about is so we're focusing on the class of finitely generated structures. And generally these are quite simple structures. But we're going to sort of ask, up to how simple they have to be, what kinds of finitely generated structures can be complicated, what kinds can be simple, and which kinds of algebraic classes can we find complicated structures inside of. In particular, we're going to talk about groups. We'll talk about fields and rings a little bit, but mostly we'll talk about groups. So the general outline, we're going to start by talking about Scott sentences of these finitely generated structures. Right, so this is, in a sense, how hard is it to describe a finitely generated structure among all structures? Once we talk about that, second we're going to talk about a notion of universality, but within the class of finitely generated structures. So when is a class of finitely generated structures sort of universal among finitely generated structures? And finally, we're going to talk about quasi-Scott sentences. So this is, we're trying to describe a finitely generated structure, not among all structures, but just among other finitely generated structures. So we sort of give ourselves a free, part of our description is to say it's finitely generated, and then after that, how complicated is it to describe the structure? So sort of the first and third part are sort of kind of similar, and the way the second part ties in is we're going to sort of use that in the third part. So we'll start with Scott sentences. So first we should talk about the logic we're going to use. So we're going to use the infinitary logic L omega 1 omega, which lets us have countable conjunctions and disjunctions, but finite quantifiers. And we can put all of these formulas in a hierarchy. So we call them either sigma alpha or pi alpha. And really we're only going to go up to alpha equals 3. So we don't need any, we don't need alpha 4. We don't need infinite ordinals. So the way we do this, we start out with the finitary quantifier free formulas, and these are at the 0 level. And then we let ourselves move up a level by adding disjunctions or conjunctions and quantifiers, right? So if you add disjunctions are like existential quantifiers, and conjunctions are like universal quantifiers. Anytime you add one of these, you move up a level, right? And you're counting the number of alternations. So, so sigma 1 things are really existential things, pi 1 are universal things, sigma 2 are an existential, then a universal quantifier, and so on. Right? So we're sort of giving ranking these by their complexity. And some examples for describing structures with these. So you can get more than what you can just get with first order logic, right? So if you're looking at the class of torsion groups, this is not an elementary class, but you can describe it with a pi 2 sentence, right? So basically you say for every element of the group, it's torsion of some order. And this is a pi 2 sentence. If we look at vector spaces over the rationals, we can now describe the dependence relation, right? So 3 things are dependent on each other. If there's some non-zero triple of scalars, that gives you a non-trivial linear dependence, right? So this is a sigma 1 formula, right? And again, the infinite conjunction is really infinite here. So you can get a sigma 3 sentence that says that a Q vector space has infinite dimension. All right, so you say for some n, has finite dimension. So you want to say for some n, which is going to be the dimension, there are n things that span it. Right? So if you have n things that span it, then your finite dimension less than or equal to n. You can also sort of invert that, right? You can say that a Q vector space has infinite dimension by saying for every n elements, for every n, there are n independent elements, right? So that's saying it's for every n, it's dimension at least n, which says it's infinite. So the interesting thing here, right? All of these. So I guess the second one was a formula, but the first one was a sentence. It doesn't actually describe any particular group. It just describes a class, right? And there's the class of all things of finite dimension. There are many structures in there, but this last one describes one specific countable structure, right? So if we restrict our attention to countable structures, there's only one infinite dimensional Q vector space, which is the one of countable dimension. So this is sort of an interesting general phenomenon, which is sort of the Scott sentences, right? So it's based on this theorem of Scott, which says that anytime you have a countable structure, you can come up with some infinitary sentence phi so that the models of phi are exactly the countable structures isomorphic to A. Right? So phi really just picks out A among all countable structures. Right? And we're going to think of phi as a description of the structure A. So here we have another example. So if you look at the natural numbers just as a linear order, you can write down a pi3 Scott sentence. Right? So first you say it's an infinite linear order. And then basically you're saying that every element is some iteration of the successor. Right? So it takes some quantifiers to say, what is the successor, but you basically say every element is some iteration of the successor element from sort of an empty linear order. Right? So we see, you have some structure and you come up with some sentence. Here we have a pi3 sentence for this structure. And then a natural question to ask is this the simplest sentence that you could come up with? Right? So we came up with this pi3 sentence. Could we come up with a pi2 sentence, a sigma2 sentence, something simpler? And you can sort of think of the simplest sentence describing the structure as being a measure of the complexity of that structure. Right? So by looking for the simplest sentence, we measure the complexity of some structure in terms of how hard it is to describe that structure. And this is this idea of Scott rank. So this is not the original definition of Scott rank, but it's a nice one that sort of ties in with all sorts of different equivalent definitions. So we say that the Scott rank is the least ordinal alpha, so that A has a pi alpha plus 1 Scott sentence. Right? So you're just measuring, where in which ordinal do you require to get some description with that rank. So the nice thing, right? So there's these equivalences. So say you have a countable ordinal. It's the same thing to have a pi alpha plus 1 Scott sentence, right? So this is something about describing A relative to other countable structures. That's the same as saying that the orbits of things in A under automorphisms are nicely definable at the level sigma alpha, right? So that you have this sort of external characterization about the structure A relative to other structures, and it's equivalent to something about sort of A internally, right? How hard is it to decide how A moves under automorphisms? And it's also equivalent to A being uniformly bold-faced delta alpha categorical without parameters. So this is a mouthful. So basically what we're saying is, so you're gonna sort of move up onto a cone, and then it's easy to find isomorphisms between different copies of A, and easy being measured by this ordinal alpha. Right, so that's sort of saying, so the first one is saying it's easy to describe A, or how hard is it to describe A? The second one is how hard is it to understand A under automorphisms? And the third one is how hard is it to find isomorphisms between different copies of A? So these are all equivalent, right? This is just sort of a flavor of what it means to try to measure the complexity of the structure by the Scott sentence. Now what's going to happen here when we look at only finitely generated structures is everything has a Scott sentence that's really low down, right? It's sigma 3. So it sort of makes sense not to talk about Scott ranks, but to talk about more finely about, is it a sigma alpha sentence? Is it a pi alpha sentence? Right? If we look at the Scott rank, we're only asking about pi alpha plus 1, right? It's only pi Scott sentence we're talking about. Here we want to talk about, sigma, pi, exactly where in the hierarchy it is. So everything has a sigma 3 Scott sentence, and it's not hard to see why. So this is sort of something that'll come up all the time with finitely generated structures, is say you pick a generating set for the structure, right? So a finite tuple that generates the structure. That means that every element can be made from that generating set using some term, right? Some combination of whatever functions are in the language. And so basically you can describe the structure by describing all of the terms in the generating set. Right? So basically you want to say that there is some tuple that generates the structure, right? So there is some tuple for all other elements. They are generated in some way. That's a sigma 3 sentence. And then you want to say, and I'm going to describe to you the atomic type of the generating set. Right? If you know the atomic type of the generating set, that tells you everything about all the terms that are built from it. So basically, right, your sigma 3 Scott sentence is saying, I am finitely generated by this tuple, and this is what the tuple looks like. But often there's actually a simpler Scott sentence. Right? So if you look at a particular structure, you say something about the structure in particular, you can come up with something better. So let's give some examples in the class of groups. So maybe the first natural group to look at is the integers. So what are we going to say about the integers to describe them? So first we're going to say they're a torsion-free abelian group. Second we're going to say, so I guess we should say what are the axioms for torsion-free abelian groups? I think they're probably all pi 1. At worst, they're going to be pi 2. For any two elements, there is an element which generates both. Right? So this is saying that you're a rank 1 group, right? You're a subgroup of the rationals. And to say this, you have to say, for any two elements, there is an element, so that's pi 2. And then third, we want to say, right, so this is saying we're a subgroup of the rationals. Now we want to say, there's this element 1, which has no divisors, right? So that you're generated by this single element 1. So we want to say there's an element with no proper divisors, right? So there exists some element, it's not 0. And for anything that might be a proper divisor, it's not. Right? So this is a sigma 2 sentence. So what we've got is we've got a pi 2, and a sigma 2 sentence. And you take the conjunction of all of these. So, right, so this is both a sigma 3 and a pi 3 sentence. But we want to say something a little bit better about exactly what kind of sentence we're going to describe this as. And we call these the d sigma 2 sentences. So d sigma 2 sentence is a conjunction of a sigma 2 and a pi 2 formula. Right? The idea is you're really taking a sigma 2 thing and then taking away a sigma 2 thing, which is the d is for difference. And then we can draw what does the hierarchy look like of these sentences sort of low down. So d sigma n is bigger than both sigma n and pi n, right? And then it's contained, you have the things that are both sigma 2 and pi 2, for example. Those things contain all the things that are d sigma 1. But then we have this theorem of Miller, which says that if you have a structure that has both a pi 3 Scott sentence and a sigma 3 Scott sentence, then it actually has a d sigma 2 Scott sentence. Right? So this is saying, right, if you're in that sigma 3 and pi 3, you have both a sigma 3 and pi 3, then you actually move down to the d sigma 2. Right? So these single arrows basically don't exist for Scott sentences. And so we'll be spending most of our time, right? Remember, everything has a sigma 3 Scott sentence. And so this theorem says if you also have a pi 3 Scott sentence, then you actually have a d sigma 2 Scott sentence. Right? Or if you have a sigma 3 and a pi 3, then you actually have a d sigma 2. So we'll be spending most of our time looking at the difference between here and up here. So there and there. So remember from the previous slide, and I'll just put those axioms up again, that is a d sigma 2 Scott sentence. So the integers as a group have a simpler Scott sentence than they might have, right? We know they have sigma 3, they actually have d sigma 2. Let's look at another natural group. So let's look at the free group on 2 elements. And to write down this description, you need to know a little bit about free groups, about Nielsen transformations. But I'll just describe what the axioms are in case you know how those work. And if not, then you can just see that it is, in fact, a d sigma 2 sentence. So first, right, to describe the free group, we say first, it is a group. Second, we have to say that anytime you have any finite set of elements of any size, it's actually generated by just 2 elements. Right? So this is obviously true in the free group. And this is a pi 2 sentence, right? You're saying for every set of elements, there exist 2 elements that generate it in some way. And the last thing is sort of the more complicated one. So you want to say anytime there is a 2-tuple, so there's 2 elements, and they look like, so they have no non-trivial relation. So right, they basically generate a copy of the free group. So you want to say that the 2 elements, right, they generate a copy of the free group, and basically you want to say that they are, something that says they are actually the generators of this group. Right? So how do you say that these 2 things actually generate the group? Well, you say basically that anytime you have some other tuple, the only way to generate this tuple from this tuple is through Nielsen transformations. Right? So you're basically saying that any 2 tuples, that there's this sort of nice 2-tuple that can only be generated by other tuples that are free. Right? So this requires some knowledge of how Nielsen transformations work. But if we just look at this, we're saying, right, there exists some tuple, and it cannot be generated, right, as by any tuple y in some particular way. So there is some tuple, it can't be generated as sigma 2. Right? So we have pi 2, sigma 2. So this is, again, a d sigma 2 Scott sentence. Right? So we found 2 natural groups that had simpler Scott sentences than we thought they might. And actually, people started to look at all sorts of different kinds of groups, abelian groups, free groups of any finitely generated size. I guess I should say that these are all finitely generated. So finitely generated abelian groups, finitely generated free groups, and so on. nilpotent groups, polycyclic groups, lamplighter groups, so all these groups that come from sort of geometric group theory. People looked at them all, and they all had d sigma 2 Scott sentences, right? And then the natural question, when every example you look at has something true, right, is it just the examples we're looking at, or is it actually a fact that every finitely generated group actually has a d sigma 2 Scott sentence, right? So we had this theorem in general. Structures have sigma 3 Scott sentences. For something like groups, can we always make that d sigma 2, in fact, right? Basically, can groups be complicated as they might be allowed to be, or are groups always like somewhat simpler? All right, so that's the question that we're going to talk about for the first part. And maybe the first step is to try to say, well, like, what does it mean to have a d sigma 2 Scott sentence? How can we figure out whether some structure has one or not? And so we get all these different conditions that are all equivalent. So, right, the first is, so the second one obviously is having a d sigma 2 Scott sentence. The first one is having a pi 3 Scott sentence. Remember, if you always have a sigma 3, if you also have a pi 3, then you have a d sigma 2. A is the only model of its sigma 2 theory, right? So obviously a d sigma 2 Scott sentence is contained within the sigma 2 theory. I mean, you have to think about how it reverses. But then, so these next two, so I guess the first set is kind of due to, at least the first two are due to Arnie Miller. The next couple about these generating tuples is joint work of Julia and Alvear and McCoy, right? So these two are saying that the generating tuples of this structure are easy to describe in some way. So they can be described by a pi 3 sentence, or sorry, a pi 1 sentence, right? So if you can describe a generating tuple, then you can describe the whole structure. And this makes sense, right? Because we saw at the very beginning, if you have the generating tuple fixed and you describe it, then you describe the whole structure. So this is sort of saying if it's easy to say what the generating tuple is, we know it's easy to say what the structure is. And the last one is saying that, so this is the joint work with me and Turbo. It's equivalent to say that A does not contain a copy of itself as a proper sigma 1 elementary substructure. So if you take A, if you can find a copy of A inside of itself that sits in there in a nice way, then that means that A is hard to describe. Right? In some sense, it's hard to differentiate the copy of A on the outside from the copy on the inside. And so the proof, so I'm going to talk about the proof between the second point, so having a d sigma 2 Scott sentence, and the last point, because it's kind of nice. It's got a nice little picture. So the one direction is, say that A doesn't have a copy of itself as an elementary substructure. We just need to come in and write down some d sigma 2 Scott sentence. So what we do is we say, let's take the pi 1 type of the generating tuple for A, and we're going to have a sigma 2 and a pi 2 formula. So the sigma 2 one is going to say there is some tuple satisfying this type. And what this says is, so because we took the pi 1 type, this says that anything satisfying this sentence will have a copy of A as a sigma 1 elementary substructure. And the second thing is we say, anytime you have any tuple satisfying this type, and any other element y is generated by x. So this is saying that anything satisfying this type P actually generates the whole structure. So I think it's clear why this, if you satisfy this sentence, it's clear why you're a copy of A, right? You have something satisfying P, and anything satisfying P generates the whole structure. The slightly harder thing is to see why does A satisfy this sentence? And this is because it doesn't contain a copy of itself as an elementary substructure, right? So in A, anything satisfying this type P actually generates all of A. So this one is not so the interesting direction, right? You just write down this sentence. I think the really interesting direction is this next one. So it's got a nice picture. So the idea is we're going to assume that A does contain a copy of itself as an elementary substructure. So here we have A. Let's call this A1. And here we have another copy of A. And we can think of this copy as elementarily embedding inside of this copy, right? So this is a sigma 01 elementary embedding. Now, of course, right, A0 is also a copy of A, so it has a copy of A inside of itself. And we get sort of descending copies all the way down. But the trick is you say, well, this copy of A, this biggest one, it could itself be a copy of A inside another copy, right? So you can think of this picture as looking like this. And then why can't this one be the copy of A inside some other copy of A? So you get A3. And then you keep on going, right? You make A's all the way up. And at the end, you get some limit structure, A star. So the first thing to notice is A star is not finitely generated, right? If A star was finitely generated, maybe by this guy, and this guy, that's 3 elements. They would lie in 3 different structures here. And so then A star would actually be, this structure. But it's not because it has more and more elements. So A star is not finitely generated. But the other thing to notice is that A star has the same sigma 2 theory as A, right? We have a sigma 1 elementary chain. And so any sigma 2 sentence or pi 2 sentence about any of these structures gets moved up to A star. So we've just constructed a structure that's not finitely generated, and it has the same sigma 2 theory as A. That means that, right, so it's not finitely generated means it can't actually be isomorphic. And that means that the A doesn't have a d sigma 2 Scott sentence. Right, so we've played A off against this infinitely generated copy of itself. All right, so now we know something about what it means to have a d sigma 2 Scott sentence. So we should look for something that does or doesn't have one. And so if you sit down, you have this idea of what we need to do. We need to build a copy of a group that sits inside of itself in a nice way. And then you sit down and you try to build one, and it turns out that you can build one. So you can make a finitely generated group G, which doesn't have a d sigma 2 Scott sentence. Right? So you should think of this group as a group that's complicated. It's as complicated as any finitely generated structure can be, but within the class of groups. To make G, you use small cancellation theory and H and N extensions. So the small cancellation, you have some idea of what you want G to look like. And then small cancellation theory sort of says, like, OK, you can actually build it the way you can, and you can check things in a reasonable way. Now, moving on from groups, right, we can think about what about other kinds of structures. So natural one to think about is rings. But if you just do this, there's this group ring construction. And it just sort of, you take the group G from here, and you make a ring out of it, and it has the same properties. So there's also a ring that's complicated. Another kind of structure we could think about is fields. But it turns out that every field has a d sigma 2 Scott sentence. And I think I'm going to skip the proof, but the basic idea of the proof is that if you have a field inside of itself, they have the same transcendence degree. It's actually an algebraic extension. And algebraic extensions are sort of very simple to describe. So what this is saying, right, so fields can't be as complicated as groups or rings can. They're always somewhat simpler. Right? And it makes sense. For fields, you have this very strong structure theory about what a finitely generated field looks like, right? You've got some transcendental elements, it's got some algebraic extension of that, and that's quite simple. All right, so some open questions from this part of the talk. So we did finitely generated groups. So a natural extension is to talk about finitely presented groups. So you put some limits on what your group can look like. Can it still be very complicated? What about commutative rings or integral domains? So the group ring is sort of, almost cheating, right? You get this really ugly ring that's not commutative. It basically looks like a group. But most nice rings that you care about are commutative or integral domains. And this commutative ring one in particular, I've tried to do for maybe 6 months now, and I still haven't done it. So if anyone has any ideas, then it would be great to talk about it. Then integral domains, I imagine integral domains, they have some nice structure theory just like fields do, so I wouldn't be surprised if they're all quite simple. All right, so we have this, we just talked about Scott sentences. So we're going to move on to talk about, right, we said that finitely generated groups can be quite complicated. And the way we proved the theorem is basically we wrote down a structure that we wanted in some other language, and we said, how can we turn this into a group? Right? So we wrote down some complicated structure, and we said, how can we turn this into a complicated group? And this reminded us of this idea of universality. So we'll actually sort of talk about a little bit more computable structure theory. So of course, right, computable structures all have domain omega. Structure is computable if its domain is computable, the functions are computable, the relations are computable. And anytime you have 2 computable copies of the same structure, they're isomorphic, but they might not necessarily be computably isomorphic. Right? So you can have isomorphic structures, but not computable isomorphisms between the 2. And I'm just going to give an example of something that has been studied a lot, right? So computable dimension. We're actually going to talk about computable dimensions. It's just going to sort of be an example of what's going on. It's the number of copies of the structure up to computable isomorphism. Right? So some old theorems say that all sorts of different structures have some kind of nice structure. They either have one copy or infinitely many copies. There's nothing in the middle for all these nice structures. Algebraically closed fields, real closed fields, right? These are structures with very nice structure. On the other hand, if you just care about any structures at all, you can come up with things with finite computable dimension, right? And of course, Goncharov did this. For any number, there's a computable structure with that dimension. And so then a natural question, right? You have this structure. You built it with some weird way. The question is now, can you do the same construction inside of all of these different classes, right? Can you make a graph with that, a lattice, partial ordering, two-step nilpotent group, an integral domain? Can you move that construction inside of all of these special classes? And these people, sat down and they did this, but every time you have, some kind of property, and you have to do this again by hand each time. And so Hirschfeld, Kusanov, Shor, and Slinko noticed this, right? So I just want to put this quote up here because it's sort of a nice summary of what's going on. So basically, anytime you have a structure with a particularly interesting computability theoretic property, you want to ask whether the same property can be found within all sorts of well-known classes, right? So here we had an example of a property, and we looked at all these different classes, and we saw what happened. And one thing you could do, if you want to say, yes, you can move it into this class, right? You just adapt the original proof into the new setting, and you work within whatever structure you're looking at. But the problem is you're sort of duplicating the effort, right? There's this original construction. You have to do all that same construction again, plus a little bit more, right? It's kind of boring. You're just saying, OK, does it work? And what you really want to do is you want to sort of have some way of coding the original structure into your new class in some way that maintains all the properties that you care about. And so what they did in this paper is they gave some ways to translate copies of some structure in one class into structures in another class that was sort of nice enough that it maintained all of the properties that you care about. Right? And that means that anytime you have a structure in this class, you just translate it into whatever structure in this class, and you just check that the property is maintained. So then what they proved is that any of these classes, and these were the nice classes, the classes from before that had things of finite computable dimension, you say is complete with respect to. So what that means is any structure with any of these properties below, you can find a copy of a structure in each of these classes that's the same, right? So anytime you find, so before we said anytime you find something with a computable dimension, you can find like a lattice with the same computable dimension, and so on, right? For any of these properties. So these were the ones that they had in their paper. And then later, people added all sorts of other things, so like degrees of categoricity, Scott ranks, categoricity spectra, and you can imagine that this just keeps going down off the page, right? Anytime anyone has some reasonable computability theoretic property, it can be added to this list, right? And the problem is you can just keep adding more properties. Anytime you add another property, theoretically you should go back to the construction. You should look at the construction, check, does the property get moved forward through the construction. And instead, what you want to do is you want to say, like, I'm going to do the construction once, and I'm going to say something about like what type of construction it is, and then I know that properties are automatically moved across. And so there are two solutions. So one is from this paper of Miller, Poonen, Schoutens, and Schlappentalk. And what they said is why don't we use computable category theory, right? So we're taking structures, we're transforming them to some other structure. Why don't we try to think of that as a functor? And what they showed is that there's a computable equivalence of categories, right? So this is sort of like functors, a functor that turns a graph into a field and a field into a graph in a nice way, right? So it's like they're kind of inverses to each other. So I said there's a computable equivalence of categories between graphs and fields. What this means is anytime you have a graph, you turn it into a field, and the field sort of turns back into the graph in a nice way. And then what you prove is you prove that a computable equivalence of categories maintains properties that you care about. Right? They also went back and looked at the old transformations. They said the old transformations, right, or I guess I don't know if they did necessarily, but you can look back at the old transformations and say, look, the old transformations are also equivalences of categories. Right? So you've got this sort of more theoretical framework for these transformations. The other solution was due to Montalban. What he said is, why don't we think about these as effective bi-interpretations? Right? So And then he proved that basically if two structures are bi-interpretable, then they're essentially the same from the point of view of computable structure theory, right? So, for example, maybe we talked about Scott sentences. So if you have an optimal Scott sentence for one, then you get an optimal Scott sentence for the other at the same level of complexity, right? So, and then if you go back and you look, all the original transformations, those all made computable bi-interpretations. So we've got two solutions, what it means to be universal in some sense. And it turns out these two solutions are equivalent to each other. So I'm going to talk about, for the next little bit, about what these solutions actually are and in what sense they're equivalent to each other. So first, let's say what is an effective interpretation? So the idea of an effective interpretation, so you're saying a structure A is interpretable in structure B. Basically what that means is that you can find a copy of A inside of the structure B in a nice definable way. So how do you find the structure A? Well, first of all, you have the structure B. You have to say, what is the domain of A? What are the functions on A? So the domain is so what makes this an effective interpretation, and what makes it different from just the normal model theory interpretations, is that we're going to allow ourselves to use tuples of arbitrary size, right? So in model theory, you say, I'm going to fix, I'm going to use tuples of size n. Here we're going to let you use tuples of length 1, 2, 3, 4, all in the same interpretation. So the domain, right, is a bunch of tuples from the original structure, and you use equivalence classes, right? So you can say, okay, these two tuples, those are really the same element of A. And then you have to say, what are the relations of A inside of the structure B? And to make it effective, these should all be nicely definable, right? So we're going to ask for delta 1 definitions of all of these things. All right, so basically what you're saying is you're telling me inside the structure B, here's how I find A in a nice effective way, and here's what it looks like. All right, and so one interesting thing, right, is if you have a copy of B, you can really build the copy of A, right? Because you know what its domain is, you know what the equivalence relations are, and you know what all the relations on A are. So if you have B, you can really build a copy of A. So that's an effective interpretation. So we had effective interpretation. The other side, we have computable functors. So one computable functor you should think about is you have this copy of B. If A is interpreted inside of it, anytime you have a copy of B, you can build the copy of A. This is sort of a prototypical computable functor. So to have functors, we need some kind of category. Our category is the copies of the structure A that have domain omega. And the morphisms in the category are really isomorphisms. So we're really thinking about, right, this is the category of copies of presentations of the structure A. So a functor, we're thinking of a functor from a structure A to a structure B, right? So it's taking copies of the structure A, building copies of the structure B. So it's right, for every A, it builds a B. And then anytime you have two structures A and some isomorphism between them, it builds two structures B, and it builds a corresponding isomorphism between those two. And then we say, when is a functor computable? Basically, when it's given by computable operators. So we have this way of building structures of B from A. That should be given by an operator. We have this way of building isomorphisms, right? So if you have this isomorphism between A hat and A tilde, then you can build the isomorphism between the two copies of B that come from that. And you're allowed to write this D of A, that's the diagram of A. So you get the diagram of the two structures and the isomorphism, and to build the isomorphism on this side. So this is a functor, right? You're basically saying, how can I turn structures, copies of A, into copies of B? And so an effective interpretation of A and B gives you a functor that takes B into A, right? So this was this thing, you have the copy of B, you have A inside of it, and then you just build the copy of A. And the point is that this actually reverses. So we know anytime I have an interpretation, I get a computable functor just by this sort of induced functor. But anytime I have a functor, I can actually get an interpretation. So I can go back both ways. And it's really, there's some strong tie between if I start with the functor and I get the interpretation, there's a strong tie between the two. Right? It is really somehow the interpretation that builds the functor back. So these two things are in correspondence, right? And this is not quite so what we said before, there are these two solutions to what it means to be universal. This is not quite saying that those are equivalent yet, because these are just interpretations in one way, rather than bi-interpretations. So what is a bi-interpretation? Or sorry. So effective isomorphisms of functors. So here I said these are in correspondence. What do I mean by that? So if I have a functor f, right, the theorem says I can build an interpretation I. If I have this interpretation I can get back a functor in this sort of induced way. So I can build a functor, we'll call it fi. And then in correspondence means that the f and fi, they're not necessarily going to be equal, but they're going to be isomorphic in some nice way. So what does it mean for them to be isomorphic? All right, so okay, saying when is f effectively isomorphic to g? And this is going to be witnessed by a Turing functional, which basically is going to build, right, so let's look at what's going on. So if I have a copy of B, yeah, so if I have a copy of B, right, I get two copies of A. And so what I want to do is I want to actually be able to build from B an isomorphism between these two. So this lambda is going to give me an isomorphism between those two. Right, so this is basically saying, if I have B, I build these two copies of A. I can figure out how to get between those two copies of A in a nice way from B. But moreover, we have some diagram that commutes. Right, so if I have A, I can build. I think the A's and B's are switched in this diagram, right? So I said I had a functor from B to A, and now I'm writing as a functor from A to B. So in the either think of it as a functor from A to B, or switch all the A's and B's in the diagram. So if I have A, I can build a copy of B and another copy of B, right? And so what we said is I get an isomorphism between those two. But moreover, if I have some other copy of A, and I have some isomorphism between the two copies of A, well, first of all, I can build those two copies of B from that other copy of A, right? And I can build the isomorphism between those two. And then what I want to be able to do is I also want to be able to figure out what happens to this H, right? So this H goes from A to A tilde to A hat. So it should induce things, right? F should induce something going there, and G should induce something going there. And then I want to know that this diagram commutes, right? So that the lambda really does know something about the isomorphisms as well. And if you have this whole diagram set up, then really F and G are basically the same, right? Because I have a really nice way to translate between the two in some effective way. So this is sort of the best you can hope for. So this Fi and this F, right? Those are, you can translate between them in this nice way. Now let's talk about bi-interpretability. So you have two structures, A and B. They're bi-interpretable. So first of all, each one is interpretable in the other, right? So A can be interpreted in B, B can be interpreted in A. But you need a little bit more. So the problem is if you just ask for that, then the two don't necessarily have, for example, the same automorphism group, right? So you want to say something about how, right? If two structures are bi-interpretable, they should be the same, which should mean they have the same automorphism group. So what do we ask? Something extra. So you have B, right? A is interpretable in B. That means that the A sort of lives inside of B, right? You can think of it as this domain of A inside of B. But then we also know that B lives inside of A, right? And so in some sense, B lives inside of A, which lives inside of B. So B lives inside of B. And if B lives inside of B, then you can think about, well, there's this isomorphism, right, between B and the copy of B inside of it. And what we're going to ask for is we want that to be nicely definable. So you can sort of, right, you can figure out how this copy of B sits inside of itself. And of course, similarly with A and B interchanged. And this implies that automorphisms of A and automorphisms of B sort of induce each other, and you get an isomorphism between their automorphism groups. So this is bi-interpretability. So basically, the two structures can be built from each other in a very nice way. On the other hand, we have some equivalent notion in terms of computable functors, which is a computable equivalence of categories. So what this is we have functors going both ways, right? So this is like, you have bi-interpretations going both ways. Now you have functors going both ways. So from copies of A, you build copies of B. Copies of B, you build copies of A. And what we want is that, right, you have some copy of A, you build some copy of B. From the copy of B, you build some copy of A. We want to say that you actually basically got back to the original one, right? We want to say that these are somehow inverses. So again, you can't say that these are actually the same, but what you can say is that this whole process and the identity functor are essentially the same, right? So you say that this composition of the two is isomorphic to the identity functor, right? So basically by doing the transformation one way and then the other, you haven't really changed the original structure. And so this is known as an equivalence of categories, and we say computable because we're asking that everything is computable. And then once again, effective bi-interpretations between the two structures are equivalent to effective equivalence of categories between A and B. So just like functors were the same as interpretations, bi-interpretations are the same as equivalences of categories. And remember that these two things are the two things from those two solutions, right? There was the solution for the fields where we said we should use equivalences of categories, and there's the solution that Antonio had where he said we should use bi-interpretations. And these are the same solution, really. So in some sense, this is what we're going to talk about is our notion of universality, right? So some class of structures is universal if any structure can be moved into that class up to bi-interpretation, right? And then you have to check, okay, bi-interpretations maintain all of these computable structure theory properties that we care about. I also want to add, so you can also think about non-effective bi-interpretations, and basically everything just I don't know if it's a word, but everything goes to the non-effective context. But you also get an equivalence with the automorphism groups of the two structures being the same.
When you say continuous, do you mean homeomorphic?
So I think any continuous isomorphism ends up being homeomorphic. There's some theorem that says all you need is continuous one way. Okay, so I said when you're universal, basically every structure is uniformly bi-interpretable into this class, right? So this class really has any structure you have. There's some structure in this class that looks exactly the same as far as we're concerned as computability theorists, right? Then you go back and check, right, that all of these classes from before are actually universal in the sense, right, that the transformations we had actually gave bi-interpretations. Right, so we have all these classes universal. Sometimes you have to name some constants, right? So for example, things like groups most groups have automorphisms. Not all structures have automorphisms. But if you allow yourself to name some constants in a group, then you can get rid of automorphisms and make them rigid. Of course, some classes are not universal, right? So we know there are structures with finite computable dimension. So if you have a class where that can't happen, then that class can't be universal. So these are all the classes from earlier on that can't be universal for this reason. So then the question is, what do we do for finitely generated structures? Of course, they're never going to be universal, right? So every finitely generated structure has a sigma-3 Scott sentence. Of course, there's lots of structures that don't have a sigma-3 Scott sentence, right? Finitely generated structures are too simple. So we sort of restrict our view of what structures we have to move into this class. So we say that a class of finitely generated structures is universal among finitely generated structures if anytime you have a finitely generated structure, you can move it into the class. You can find something in the class that's essentially the same. So we know fields are not universal among finitely generated structures. Why? We move through Scott sentences. Fields all have d sigma 2 Scott sentences, right? That's some property of fields that's not true in general of finitely generated structures. So fields can't be universal. So we thought about what was happening in our construction earlier when we talked about Scott sentences. So what we did is we said, how are we going to build a structure that we want? And then how are we going to turn that into a group? And so then what we said second is, well, say we have any structure, not just that one we built. How do we turn that into a group? And if you look at the construction, you have to adapt. So there are a couple things that were just for that particular structure. But if you adapt it all, you end up finding that finitely generated groups are actually universal among finitely generated structures. And you have to name 3 constants is what our construction does. So of course, you have to name constants because, as I said, most groups have some automorphisms. Lots of structures don't have any non-trivial automorphisms. So if you're going to reconcile those, you're going to have to name some constants. Another thing we want to have is, so there's these constants, and we don't really care about finitely generated groups with 3 constants named, right? That's not like a natural class. So for most computability properties, we want to say something about the group without the constants. And it's pretty helpful for this to say that the constants are nicely definable, right? Of course, they're not going to be delta 1 definable, so pretty much the best we can get is sigma 1 definable. So anytime we have some property right now, like we had before, instead of constructing a finitely generated group, what we do is we just construct some structure that's finitely generated, we transform it into a group, and we make sure that whatever that property is maintained by that transformation. All right, I think I might skip this. So basically what this is saying is that when you have a Scott sentence, you can add or remove constants from the structure without affecting the Scott sentence, right? The complexity stays the same. Remember here we said that the orbits are sigma 1 definable of the constants. So you need that for one direction. But basically this is saying that the Scott sentences stay the same. Actually, so maybe you should say, right, so groups, we know we're not going to be universal because of this problem with the automorphisms. So like we said that fields are not universal, but really we should say something about fields with constants, right? So how do we say that fields are not universal even after we add constants? Well, this lets us do it, because if you have some structure with no d sigma 2 Scott sentence, and you turn it into a field and you name constants, this is saying you can get rid of the constants and you still keep or you can add constants and you still keep the d sigma 2 Scott sentence. So fields are still not universal even if we add constants. That wasn't some sort of weird thing that was going on. So now we have this whole way of taking finitely generated structures and moving them to the class of groups. So we should really have some kind of property to sort of experiment on, right? We should make sure that this transformation actually does something that we have things we can use it for. So our thought was to look at quasi-Scott sentences. And the motivation for this is really looking back at this construction here. What we were doing here is we were playing off this finitely generated structure A with this infinitely generated structure A star, right? And the reason that A didn't have a d sigma 2 Scott sentence was because it looked like this one. So that's not necessarily what we care about, right? What we might care about is we have all these finitely generated structures. How do we distinguish A from these finitely generated structures? So this we do with quasi-Scott sentences. So a quasi-Scott sentence for a structure is a description of the structure, right? So it's a sentence phi, and A is the unique finitely generated model of phi, right? So here it's fine if there's some infinitely generated structures that satisfy the same sentence, as long as this structure is the only finitely generated one. So actually, you immediately get something out of this restriction, which is that every finitely generated structure now has a pi 3 quasi-Scott sentence. So what does this pi 3 sentence say? So you take the atomic type of a generating tuple of A, and you say that every tuple is generated by a tuple of type of this same type. So what's going on here? I think first of all, it's clear that the structure A satisfies this sentence, right? Because A is generated by something with this type P. So of course, every element in A is generated by this type P. So the question is why, if you have a structure where this sentence is true, why does it have to look like A? So say we have some structure B, and B is a model of this sentence. So I'll call this sentence phi. So what do we know? We know that every tuple is generated by a tuple of type P. So let's just pick some element. We know this element is generated by a tuple of type P, right? So there's something of type P which generates this. And then we can say, here's the substructure, right? Let's call this element G1, right? And it satisfies the type P. And here we build the substructure generated by G1. Now, the substructure generated by G1, that's isomorphic to the structure A, right? you had this type P that basically said anything generated by something of this type looks like A. All right, so two cases. So if this substructure is actually all of B, then we're done, right? Then B looks like A. So the only other possibility is that there's somebody else here who's not in the substructure. Well, then what do we know? We know that this element plus G1, that's all generated by something that satisfies the type P, right? So there's some G2, which generates both this and this. And then we can take the structure generated by G2. Right? Again, we know it's isomorphic to A. Okay, again, right, either this is the same as this structure, or there's some new element here, right? Then we get a G3, generates this, and we build a structure there. So, right, either this stops at some point. If it stops at some point, then B looks like A, or it keeps on going, right? If it keeps on going, what do we know? Well, we know that B is not finitely generated. So, right, what we've done is we said, okay, either B is going to be finitely generated, in which case it's isomorphic to A, or it's not finitely generated, in which case we just don't care about it at all. All right, so we still also have a sigma 3 quasi-Scott sentence, right? Every Scott sentence is also a quasi-Scott sentence. So we now have both a sigma 3 and a pi 3 quasi-Scott sentence. All right, so one thing we want to know is, again, that we can use this universality to deal with quasi-Scott sentences, right? So we want to do something where we build something with no simple quasi-Scott sentence. We want to say, okay, we can get a group that's the same. So the first thing is, say we have it's basically saying we can add and remove constants, right? So again, we use this fact that the constants are nicely definable, which was true for our groups. And so A has a quasi-Scott sentence of some complexity, if and only if A with the constants does. So we can add or remove constants, and we don't change what kind of quasi-Scott sentences there are. The second thing says that if A and B are effectively bi-interpretable, plus there's a little bit more that you need, which is true for groups, so that this does apply to groups, then A has a d sigma 2 quasi-Scott sentence if and only if B does. Right? So we can move simple quasi-Scott sentences through bi-interpretations, if the bi-interpretations are especially nice. The problem here is that bi-interpretations don't maintain being finitely generated. They only maintain being finitely generated by delta 1 definable things. So there's some little complexity there. Okay, so right, we want to say, when does a finitely generated structure have a simple description in terms of quasi-Scott sentences? And things are a little bit more complicated than they were before. So it's somehow easier to look at sigma 2 theories here. So you get something like before, where the sigma 2 theory has more than one finitely generated model, right? So here we're thinking of the sigma 2 theory kind of like a quasi-Scott sentence, but it might not actually be a sentence. If and only if you have this sort of image where A is inside of A, except now A is inside of B, which is inside of A. Right? So you can sort of do the same argument here, but now the A's and the B's are going to be alternating. So this is how you find a complicated structure in this sense is you now have to find A's inside of B is inside of A. All right, so we can take this and we can say, okay, well, we'll build something like this, right? You're thinking of A is inside of B is inside of A, and you go and you build one. And it actually looks quite similar to the group that we built, just as a general structure. So one thing that's interesting is you can, so this has the sigma 2 theory has more than one finitely generated model, but actually has no d sigma 2 Scott sentence. So we sort of separated things at an interesting level there. One thing this shows is you can have a sigma 3 and a pi 3 quasi-Scott sentence without having a d sigma 2 one. Right? So this thing about Scott sentences where they move down like that is not true for quasi-Scott sentences. All right, so we built some general structure. It was some kind of tree with unary operators. So now you say, okay, I'm going to turn that into a group, and you get some group that basically is quite complicated, right? Its sigma 2 theory is not enough to distinguish it from other things. So even for quasi-Scott sentences, right, there are complicated groups. So this theorem said when is the sigma 2 theory sort of a Scott sentence, a quasi-Scott sentence? If we're talking about d sigma 2 quasi-Scott sentences, We don't actually have a nice characterization yet. But still, sometimes, right, if you give me a structure, I can try to write down one by hand. Right? If you have some particular structure, you look at it and you say, okay, how do I describe this? Sometimes you just write down a d sigma 2 quasi-Scott sentence. So actually, we get an interesting separation. So there's a finitely generated structure that has no d sigma 2 Scott sentence, but it does have a d sigma 2 quasi-Scott sentences. Right? So Scott sentences and quasi-Scott sentences can even be separated down here. Right? Somehow, allowing yourself to say that things are finitely generated gives you even more power, even when you're talking about d sigma 2 things. Now, of course, you can turn this into a finitely generated group. Right? So there's some finitely generated group which witnesses this separation. So I think these two theorems sort of show the power of this universality, right? We wrote down what it means to be universal, and then we just went off and looked for things, and we found some places that we can apply them for. And Bach was actually also talking about, so Bach talked about these random structures, and I've been talking with him, and it looks like we can use this sort of universality to build branching classes of groups, right? So you take some branching class and you just turn it into a group, and it seems like it should also be a branching class, right? So, and there should hopefully be other kinds of properties of finitely generated structures that you can just go and apply this same machinery to, and you know, it lets you build any kind of structure and do whatever you want now in a group. So two questions we're still working on. So basically one, right, we know a lot about sigma 2 theories. And basically we want to figure out what's going on with d sigma 2 quasi-Scott sentences. And there's this little gap, right? We have this, there's sort of an extra question that we can ask there. And then we want to say, you know, are there any models that fit inside of this gap? So, right, of course, you're now thinking about general structures, and once you get some general structure that fits inside this gap, you turn it into a group. So hopefully this sort of convinced you of the power of this idea of universality and the fact that, you know, it's easier to work with general structures, and then if you have this nice way of turning things into groups, then you can just sort of start hitting all these questions with this general power. And the last thing I want to do is I just want to announce, so we're going to have a conference in June at the University of Waterloo. So Barbara Chima, myself, Laurent Bienvenu, and Peter Cholek are organizing it. If you're interested, please contact Barbara Chima. All right, thank you.
There's an old transformation from graphs into linear order. It's Friedman and Stanley. And it's always looked as if there was no interpretation corresponding. But you do get the fact that you have isomorphic groups, they go to or isomorphic graphs, they go to isomorphic linear ordering.
Yeah.
And if you somehow had isomorphic linear orderings that were of the kind that you could get come from isomorphic graphs. Is there any sense in which there's an interpretation? I mean, it looks as if there are just bits of, you know, a tuple in the graph becomes a huge number of bits of orbits here and there and here and there, all over the place. It doesn't look like an interpretation, but with this. Have you looked at that at all? Is there any sense in which you're allowing now different size tuples to correspond to elements?
So
there's an interpretation.
So I think, if I remember correctly, I think like the linear order is interpreted in the graph probably, because you build it from the graph. But I think.
You build the linear order from the graph.
Yeah, but I think finding the graph in the linear order is harder or something like that.
Finding the graph inside the linear order is what I would.
But I wonder, maybe you can do it like non-effectively. So maybe you can do it with like sigma 3 or something like.
Yeah, forget effectiveness.
Yeah.
They carried it with Borel.
So maybe like with boldface sigma 3 or something. Maybe you could define it like that.
Yeah, I mean I can't see what's the universe. I can't see it.
Yeah.
It's the elements of the universe there, right?
That's a good question though. Maybe you can do it at a non-effective level. Right, because you definitely can't do it at an effective level, but.
Yeah,
Yeah, yeah. So I think there's definitely a functor one way, right? From the graph, you get a functor to the linear order.
You get a definite linear order.
Yeah, but then the question is the functor the other way, I guess. And maybe there's like a non-effective functor the other way.
When you say that isomorphic graphs must, so from isomorphism between the linear orders, you could recover an isomorphism between the graphs, the
Yeah.
graphs, but not effective, but never mind.
Yeah,
So there should be some sort of.
that's true. Yeah.
Sorry.
Yeah, one comment is, I think it could be interesting to show that every algorithmically random structure is a high score, right? So they're all finitely generated. That would be interesting. But another question is like, so in group theory, there are famous groups like forms like solitary group. You mentioned B1N, but like BNN. Do you have anything about that? Do you know anything? Or Thompson's group?
I don't. So the person to ask about that would be Turbo Ho, he's like a group theorist who does some logic, I guess. Because I don't actually know how he proved any of those things or